Good day, y'all. A hearty welcome to those who have been following the channel Loss Prevention Maverick, which is primarily intended to elucidate concepts on process safety and loss prevention. Let's now look the topic for today, which is functional safety part 2. A disclaimer for those who are new to functional safety and who have just stumbled onto this part 2 series, may I please ask to pause it right now, go back to the part 1 series of mine where we sort of talk about what is functional safety, the differences of functional safety to process safety, workplace safety, definitions about SIF, SIL, SIS and all that. So it will be better if you could go back to that before continuing for part 2. A little bit about me. My name is Rahul Patteri. I've got a master's in process safety and loss prevention from the University of Sheffield. I'm a functional safety specialist and have got a bachelor's in fire and safety engineering. Have been a little more than 15 years into the whole concept of controlling major accident hazards. Down the memory lane, I've started as a firefighter, moved on to be a technical safety engineer for petrochemicals and offshore. Much of my learning was when I was working as a process safety consultant, and now for a tad few many years have been working with offshore and onshore operators in for major accident hazard management across the various life cycle phases. The functional safety lecture series is going to be a pretty elaborative one, and these are the concepts that we had spoken on part 1. So for those who have missed, I would again suggest to please go through the part 1 before we continue for the part 2. On part 2, that is this video, we would be talking about SIF failure states. So now let's ask the question, can SIFs fail? Yeah, can they fail? Yes, of course they will fail. Why? Because SIFs consist of hardware and software. Let's now look into a typical SIF. So here, as we see on the screen, there is a process piping, and the piping has a temperature transmitter which has a dialogue with the logic solver, and the logic solver speaks to the emergency shutdown valve, and all of them are interconnected electronically. So here the safety function that the SIF caters is that when the temperature exceeds 65 degrees Celsius, we ought to close the valve in 10 seconds. So once we design a particular SIF and then we integrate the safety function into an architecture, that goes through a FAT and a site acceptance test and gets commissioned, then that SIF is then said to be in a state called OK, which is all correct. So this particular SIF is now in an OK state. So guys, we have seen the first state called the OK state. Now let's come to speak about the next state. So here the same safety function applies to the SIF, that is when the temperature exceeds 65 degrees, close the valve in 10 seconds. Well, over the period of the process variable turned to 65 degree Celsius. So the temperature transmitter speaks to the logic solver then sends the signal to close the emergency shutdown valve. So what happens? The SIF has now executed its function, and that particular state is called a safe state. So this is the second state of SIF. We spoke about the first state, which is called OK state, and the second one is the safe state. So till now we have seen the two states, which was the OK and safe state, and now it's time for us to look into the third state, which is let's see what the third state is. So if we want to talk about the third state, let's now first look into our safety function when the temperature exceeds 65 degrees Celsius. So where is this 65 degrees Celsius actually recorded? Well, the 65 degrees Celsius, the transmitter sends it to the logic solver, and it is in this logic solver where 65 degrees Celsius is programmed. How is 65 degrees Celsius programmed? It is using the binary code, and the binary code translates 65 such as this. How do we know this? If you now know how to convert binary to arithmetic, it is like this: 1 multiplied by 2 raised to 0, 0 multiplied by 2 raised to 1, so on up to 1 multiplied by 2 raised to 6. It gives us the answer 65. But however, let's assume that this particular 0 got converted to 1 because of a bug or a software integrity issue or some sort of a cause wherein it was not programmed properly. So here what happens, now this new set of binary code translates to not 65 but 97. So which ideally means now the safety function, the temperature exceeds 65, has now erroneously been converted to 97. So now the logic solver, according to logic solver, now what happens? There is no 65, it is 97. So now what happens during operations? Yes, the process variable touches 65, the temperature transmitter does its work, sends it to the logic solver. But however, the logic solver, according to the logic solver, the condition was that when it touches 97, close the valve. So which means it has not touched 97, and it does not then translate to close the valve. Wherein what happens, the particular SIF which was designed to perform the safety function, and the safety function, that is the temperature exceeds 65, close the valve in 10 seconds, that did not happen, and that particular state is called a dangerous state. And this is the third state. The first state was an okay state, and the second was a safe states, beg your pardon, and the third state is called a dangerous state. So we saw the three states: okay, safe, and dangerous states that the SIF goes through. So this is the next state. But to talk about the next state, let's say that, well, this particular operator, in order to better have control in their safety instrumented function, actually went to have a redundant transmitter which works on the 1 out of 2 principle. So here the safety function is the same, that when the temperature exceeds 65 degrees Celsius, close the valve in 10 seconds. However, here, considering the availability of the hardware of the transmitter, there were two given into a voting principle of 1 out of 2. So when one of them sees the process variable, it needs to speak to the logic solver. So here now what happens, let's say over time one of these particular transmitters went bad, okay, and here when this process variable, the temperature, reaches 65, since it is still in the voting principle, the temperature transmitter sends a signal to the PLC, and therefore the safety function here is still executed. Why? Because there is something called as a hardware fault tolerance. All this will come later when we will talk about hardware concepts, but here the voting principle was available, and therefore though this particular error happened in one of the transmitters, still the safety function was executed, and that particular state of SIF is called an intermediate state, and that is the fourth state. So here how is the intermediate state different from the safe state? Well, if I can jog your memory, please go and understand that in both the safe state and the intermediate state, the safety function has been executed. However, in this intermediate state, it is that one of the redundant instruments have went wrong, so it needs to be repaired as soon as possible. So this particular state is called the intermediate state. So the four states that we saw: OK state, safe state, dangerous state, and intermediate state. So according to IEC 61511, they say that this particular SIF can at any point of time be in any of these states. The only thing that I would like to mention specifically is that for the intermediate SIF state to happen, it needs to have redundant devices, at least two. So now let's look into how these states translates into the process, or how does it affect the process. Ideally, our SIF is to ensure that our process is safe. So how does the SIF states, and what is the correlation with respect to its effect to process? Let's see. So what is an OK state? An OK state is when a system has been, after the site acceptance test has been commissioned, so now we know that the process is available and is protected. In a safe state, what happens? The process is stripped, so it is safe. Whereas in a dangerous failure, here the process is available, because if you can jog your memory back, we know that the PLC which was supposed to work at 65 somehow got erroneously seeking logic for 97. So now the process keeps on, is available, the operating plant is working, however it is not protected. And then intermediate state, the process is available and protected, but repair needs to be initiated. So these are the four states, and how each of these states translates itself in definition to process. We saw that the SIF oscillates between the four states, and let's ask ourselves, why does this happen? This happens because the equipment or the component on the SIF goes bad, or there is a failure. There are three types of failures in definition for the equipment, and that is, or those are, random hardware failures, common cause hardware failures, and systematic failures. So now let's proceed to see what is actually a random failure. So by definition, a random failure says that those failures which occur at any random time as a resultant of one or more possible degradation mechanisms on hardware. That is, it could be worn out, stuck, or it's broken, or sorts. So here what we have to caution ourselves is the word random, which means it happens at any point very intermittently. And then the other one is, it is a degradation mechanism. So that is a random hardware failure. Let's look at some pictures wherein the internal linings have gone, and look at the aberrations because of some internal erosion that happens. So what happens is that over time, because of some degradation mechanism on the hardware, it is called as a random hardware failure. So we have seen what a random hardware failure is. So as the term suggests, a random hardware failure happens to a SIF randomly because of some degradation mechanism. So in order to avoid this failure, so that we get better availability of our equipment, there are two ways. Yes, we can either control it or we can avoid it. But having known the definition that it is a degradation failure, we cannot completely avoid it, but we can control it. There are provisions on the code IEC 61508 which addresses measure to control. So it is told that yes, manufacturers recognize, or they deem to understand, that we cannot avoid it, but then we can control it and then better improve the availability by having a built-in feature, carrying out reliability assessments qualitatively and quantitatively for the component, yes, for the component where, for example, qualitative assessments like FMECA, a failure mode effect analysis. We will talk more about it when we come to the series on hazard analysis on functional safety, which may be possibly our part 3. But then qualitatively, the manufacturers look into what are the various failure modes that a particular component can happen, what are its effects, how can that be controlled and prioritized. And quantitatively as well, such assessments have to be done. So, for example, there are various provisions that we were seeing in the 61508 IEC code, which sort of mandatory requires the manufacturer to go through various steps so that we can improve the availability, or rather reduce the random cause failure on hardware. So there are things, see, HR is highly recommended, R is recommended. There are also guidances called as M mandatory and the like. The code IEC 61511, in order to reduce or in order to control the random hardware failure, asks us to buy IEC 61508 compliant device, and once we integrate our SIF to perform the reliability study for the entire loop. Perform a reliability for the entire loop, wherein the various probability on failures of demand are then plugged in, and we get a value on how reliable and how available our system is. So moving on from the random hardware failure, we've now come to common cause hardware failure. So let's look into the definition of common cause hardware failure, which reads that it is the concurrent failures of different devices resulting from a single event whose failures are not consequences of each other. It happens when we have redundancy. These events are primarily related to environment, such as a sandstorm, there's an earthquake, a tsunami, flooding, lightning, and electromagnetic interference and the like. Let's now talk about it by our conventional SIF. So what it says that, or rather let's now discuss, okay, we had a random hardware failure, we did a reliability assessment, and we came across saying that yes, we need 2 such devices so that we have better availability, and that was a measure to control the random hardware failure. But however, though we have these 2 things which will certainly control the random failure, but it does not make itself immune to the environment, or let's say the act of God, for say. It does not make it immune to a sandstorm, lightning, or a flood. For example, if there is a flood in this particular asset, you know, the whole area here is flooded, your instrument, if it is not as per the appropriate ingress protection, the IP code for a flood, it will not be available. Likewise, let's say there was some electromagnetic interference, there was some lightning which sort of burnt across the control cables, or maybe a sandstorm which because of either that it was a poorly designed ingress protection module, or over time maintenance was not done, there was, the gaskets were loose, and then the sand went inside into this electronics and made it not to work. So those kind of failures which are because of environment are called a common cause hardware failure. Coming into now, how do we see that there is less common cause hardware failure? Let's address those 2 words again, control and avoid. So here, yes, we know that we cannot totally avoid it, but we can only control, as it is an environmental factor leading to this failure. IEC 61508 measures to control says that provide diversity. So we said that, you know, when there is redundancy, helps us against random failure, whereas diversity is a measure to control against common cause. Let's take an example. 2 transmitters working 1 out of 2. One is a normal ingress protection case, and one is suitable for flooding. So when there is flooding, well, at least one of your system will be working, and therefore you have controlled your common cause hardware failure. The other one is the same, perform reliability qualitatively and quantitatively. IEC 61511 measure to control is also the same, buy 508 compliant devices and perform loop reliability calculations. The third failure we come across is called a systematic failure. For the keen observers throughout the series, let me just say that in the other places there was random hardware failure, common cause hardware failure, but here it is just written systematic failure. We will come to know why by let's look into the definition. It's a failure resulting in a pre-existing fault which occurs consistently at particular conditions, and this can be eliminated by removing the fault. Elimination, that is modification via some entire life cycle process, which is better design, better manufacturing, better assembly, better documentation, better operating procedures, etc. The particular failure applies to both the hardware and software alike. But something to remember here is that softwares can fail only systematically. Those softwares cannot fail randomly and what the code says is that there is no common cause failure for software. Yeah, I mean, an environment is not going to affect the software. So software can only fail systematically. So what it means is that, let's say when the system integrator is going to sort of write in the program for a particular PLC, if he makes an error or if there is a bug in that particular software which is not verified or validated, and that software is copied onto a particular PLC, and this particular PLC is then mass manufactured, one particular error or that systematic failure alone sort of now guarantees that all the particular PLCs which went through that particular assembly series will have that bug. So this is called a systematic failure. So let's follow suit again. Control, avoid. So here guys, let's wait or pause for a second and think. A systematic failure is a pre-existing condition, yes, and it is nothing about technical. There is no degradation sequence. It is not about common cause, that there is some environment that you can control. This is something that happens because of lack of functional safety management. That is, possibly the hazard was not identified properly, and this because of which the safety function was not addressed, or maybe the safety function is addressed but the system integrator's language that he used or the code was wrong, or maybe all that was right but because of some assembly process something went bad, or maybe the operating procedure was not apt for it, and therefore these kind of systematic failures can actually be avoided. And what does these codes tell us? The measures to avoid, like we said, improving the system capability through effective functional safety management, and of course IEC 61511 asks us to buy IEC 61508 compliant device. So now we've seen the SIF states, and we've seen why these SIFs kind of move across or transform onto various things because of the various failures. So here now let's now say, what is functional safety? So if someone asks us what is functional safety, well, the IEC 61511 has a definition. To be honest, it is kind of verbose, and I could not actually wrap my head around it. So therefore, I am trying to give a practical definition which is actually stated conclusively by Dr. Michael Houtemans in his course, and it says that a SIF is 100% functionally safe if all random hardware failures, all common cause hardware failures, and all systematic failures does not lead to malfunctioning of the SIF. That is, it will not be harmful for people, asset, environment, and reputation. So that is what is called as what is functional safety. That is a practical definition. So now let's say, Can we guarantee 100% functional safe SIF? Well, it cannot. Why? Because we know that there is no way of avoiding random hardware failures or common cause. It cannot be controlled. So this is where the whole definition of SIL comes to importance, because SIL is a performance standard which clarifies the performance of SIF to function on demand irrespective of all the occurrences of random, common cause or systematic. So we've come to the end of the lecture series here, then that is the part 2 of functional safety. Let's pay our credits. One and the foremost is the risknology course, for which I was a part of, provided by Dr. Michael Houtemans, and that is the course which made me the functional safety specialist that I am today, and of course IEC 61511 and 508. Have we all heard about the golden circle? A golden circle is a phrase coined by Mr. Simon Sinek. He's one of the motivating speakers or motivational speakers for businesses and the like. So let's now sort of follow suit. Why am I making this particular course? This course is because in order to give interesting, illustrative and comprehensible know-how about the topic. How do I think it has to happen? I would like to aspire more like me, who have been fortunate to be part of this industry, fortunate to have good mentors in our career, to make more of such videos and then put it in this platform so that there can be people who can gain from this, and it's free. What is this all about? This is all about bringing a community of giving. We need to give back to our community, and the best way is to democratize learning to be free and comprehensive. I always believe, now taking a segue, it is I have full faith, or I believe in the act of gratitude or an attitude of gratitude. And here I would like to pay my respects to Mr. Khalid Abdullah Al Mamari. He was my colleague when I was working in Oman with an operator. But the word colleague is too low to define our relationship. He is more like a brother to me. During my time settling in Oman, he ensured that my family is safe. He also ensured that my son, who was then 2 years old, need to be in the company of my parents, who arranged for visas and residency on the like. I am always indebted to this gentleman. Well, this concludes our part 2. Let's look forward to part 3. Thank you all for your time and patient listening.